the last speaker before the coffee break session is Tero, also from Aalto, but he's from Aalto, and the stage is yours.
Thanks. Hopefully you can hear me. Nice. So hi, I'm Tero. I'm from the physics department here in Aalto, and I'm going to talk about some Bayesian optimization that we have been doing related to multi-component alloys and glasses, so related to the previous talks today. This is in collaboration with some people in Poland and in Italy. So what were the multi-component systems that I was talking about? So high entropy alloys or multi-principal element alloys. So here we have focused on this very commonly used Cantor alloy, usually more in the equiatomic sense, but what we are trying to do is change the concentrations of these different species and see how the mechanical properties change. So the key point here is that you have this FCC structure, but you have compositional disorder. Then after that, we worked a bit on metallic glasses. So here is copper, zirconium, aluminum, where the aluminum is a smaller additive component. And here, in addition to the compositional disorder, you also have a structural disorder. So you have this amorphous structure. And yeah, to mention that we have everything is in simulations here, so keep that in mind. So what are the mechanical properties that we care about? Well, we take the sample shown in the last slide and do shearing simulations. So you just do this. We do this using lumps and somewhat small system sizes. So for the high entropy alloys, we had 1080 atoms and 6000 for the metallic glasses. But we did test for the high entropy alloys. We went 2 orders of magnitude higher and saw that there's no great changes. And with the metallic glass, we went almost 1 order of magnitude higher. What we are interested in is the yield stress, tau, and also a bit the shear modulus. So if you look at the high entropy alloy, the stress strain curve when you do the shearing, first you have linear response, and then we look at the first big drop, and we say, okay, just before it dropped, here we had the maximum stress, and we call this the yield stress, and we also take the yield strain, and the slope of the beginning part is the shear modulus. And we do this for 100 realizations of the disorder, so we make different realizations and average the yield stress over these. With the glasses, we did a slightly different thing. So, okay, similarly, we take the beginning part and take the slope of that as the shear modulus, but we averaged the stress strain curves and got this bit nicely flowing diagram, and then just took the maximum as the yield stress. So maybe this is a bit more closer to what you would have in an experimental system where you have these separate volume elements. Okay, so the key machine learning part is the Bayesian optimization. Well, this is nothing new for the people here, I think. We use just the composition space as the search space. We make some restrictions. So for example, for the high entropy alloys to have some high entropy character, we restrict the composition of each element to 5 to 35%. In the metallic glasses, we restrict copper and zirconium to 30 to 70%, and then say that, okay, the aluminum content needs to be lower than either of these. Okay, then we have our search space. We just do Gaussian process regression to map from the composition to the yield stress based on the points that we measure. Simple anisotropic RBF kernel. Okay, so then we have at each point in our, so here we have basically a grid of 1% intervals. So at each point we then have nicely a mean value for the yield stress and a standard deviation, so the measure of the uncertainty. Then we can do simple Bayesian optimization using, using some acquisition function. In one case we use the expected improvement, so to iteratively optimize. So what's the way we do this material design in some sense. So we take some initial compositions, we compute these mechanical properties, we store them in this nice AMAD database that you can access online, and also so the software can access it from the cluster that we're using, and people can also look at the data. Oh, so we have 5 more points now. Then we store an automated workflow, which is, so based on this data, the Bayesian optimization determines where to measure next, takes the maximum of the acquisition function, it computes the mechanical properties and appends the database, and then you go around this. So the idea is that you have some points here shown in red that you have measured, then you do this GPR to map the basically the surface, then based on the standard deviation, you compute some acquisition function and then take its maximum. Okay, so this is our new point. So we measure there and then keep going. In the high entropy alloy case, we use just expected improvement to optimize the mechanical properties as fast as possible. So this is the way to balance exploration and exploitation. And in the metallic alloy case, metallic glasses case, we were actually just interested in mapping the space because it's lower dimensional, so it's easier to do. So we just do pure exploration, just take the standard deviation as the acquisition function. Additionally, for the high entropy alloys, the equiatomic contour is FCC structure, so we wanted to keep this. You can do this by somehow computing the phase fraction of FCC, which is denoted by F here. There's a method called CalFAD that people use for this. I'm definitely not an expert, but it was easy to take some software that does this, and it gives you that, okay, this is at this temperature, this composition is 90.5% FCC. Cool. And as the search space is relatively small, we can actually pre-compute all these points and do it as a table lookup. And then you can see that, okay, so here this is the cumulative distribution of the FCC phase fraction. So if you are at relatively low temperatures, then not that much of the search space is FCC. The vertical line is the FCC phase fraction for the equiatomic contour. So even for our starting point, you need to go to 900 Kelvin to actually have purely FCC structures. What we realized that, okay, the database here is key, so these calculations are done based on some database. So we did this open source version and in the end we tested with some proprietary software. Might be actually better because they have better database. But so if someone wants to do this, maybe keep this in mind. So as I explained, the workflow is you start from the database, you do the Bayesian optimization, you find where to measure next, you give this point to the CalFAD, you check if it fulfills your constraint. If not, you reject and you take the next best point, the next best acquisition function value. And then you do lumps, you look at the stress strain curves, you determine what you want and you put it in your database. This is the paper where we describe this. And I find this nice that if you are trying to get your summer student to program this, that you can try to tell them that, okay, you can press enter and run the thing for 3 weeks and just go out and go to the beach. So extra motivation in that. So what we get. So here is the yield stress as a function of the iteration number. And here actually see the best value as the black line, and here is the best value plus the expected improvement that the Gaussian process thinks that you are going to have. So it's keeping in mind that this is 5-component alloy, so 4-dimensional search space. Improvement is found quite quickly at around 30 iterations. There's a great jump. It finds the correct place in the search space. And then the best that we found was at the iteration 72, but the improvement from here to here is much smaller. And here is how the composition actually evolves. And what we find that the best composition that we get, this one here is a medium entropy alloy. It's a nickel, cobalt, chromium the good mechanical properties of these alloys are kind of known. So this is what I see often happening in these type of things, that you find the optimum at the end of your search space in some corner. So maybe not so interesting. But so if you're thinking of doing this in a practical use case, maybe avoiding cobalt might be useful. People want to do that, and so having additional constraints would maybe make this better for real life use cases. I mentioned the shear modulus. If we compute that, it's very correlated to the yield stress. So optimizing for one or the other, it doesn't matter so much. So for the metallic glasses, here there's an additional thing, that the cooling rate of how you prepare your glass, it matters a lot. So here, if you look at the energy of the system with different cooling rates, and actually one different method, you can see the clear differences if you do it in a different way. We use this hybrid molecular dynamics Monte Carlo scheme for computationally efficiently doing the glass preparation process. It's a slight modification to the conventional swap Monte Carlo, but very similar. So what has to change in the workflow? In the metallic glasses case, not much. There's an ML database, so you do the same Bayesian optimization with a different acquisition function, but still. And then you do this glass preparation, which is the cooling part, which is the most time-consuming one. We do some crystallinity check that if we actually get metallic glasses. In all cases we got, so nothing interesting there. But we used only one cooling rate for this, and then after we had done our mapping, we did the exact same points for two different cooling rates. So, and then after you have your glass, of course, you do this mechanical deformation and database update. So this is the paper where we describe this. So you get this nice plot of your landscape, so how the yield stress behaves as a function of the composition. There's a single optimum around 15% aluminum and 30% zirconium. If you look at, again, the yield stress and the shear modulus, they are very strongly correlated. So this is the middle cooling rate that we had, 10 to the 12. We increased the cooling rate by order of magnitude, so we basically get worse glasses. The landscape doesn't change much. The values change a bit here, but looks pretty much the same. And then we run for a order of magnitude slower cooling rate. We only did 12 iterations because it's really computationally expensive and not much difference. So what's the cooling rate effect? So something a bit interesting. So if we plot the middle cooling rate value for the yield stress here, and here the yield stress for the other two cooling rates, when the yield stress is low, the cooling rate doesn't matter that much. All are the same, so lying on this dashed black line here. But when the yield stress is high, so when you have these good mechanical properties, then the cooling rate effect is maximal. So if you have a really slow cooling rate, you get really good mechanical properties, and with fast cooling, it's really bad. And yeah, interestingly, we find this that the shear modulus and the yield stress are linearly related at all cooling rates. In the usual experimental picture, you would have some trade-off between the modulus and the yield stress. So one more thing, that if you look at the stress strain curves for the difference, so the blue one is the starting point of copper zirconium 50-50, and then we have our worst glass here as the green one, and the best one here as the orange one. So we see that the worst glasses behave in this very ductile way, that there's no clear peak, and when we get better mechanical properties, we get this shear banding, so a big stress drop. And what we can then do is that compare, for example, these three. You look at the local structures, so we have some very small fraction of local BCC, FCC, and HCP. But what we get in this best class, we have these icosahedral configurations locally. So this is what gives you this good mechanical properties. So what we can conclude is that, okay, this is nice way to do automated composition search, even though the methods are nothing new. So people here have been talking about much fancier things, but actually using them in some practical use cases still not often done. And one must be a bit careful, because if you have this complementary nature of the yield stress and the shear modulus, it's something that's different from the experiment. So we are talking about really small systems in silico. So this might be not directly applicable to experiments. I would be interested to see when someone does the same mapping, that what it looks like. So if one wants to do something more interesting than just composition search, then you would have a larger composition space and then have some descriptors. You compute something or you do some experiment that's fast to do to characterize your material in some sense. And there, what we found is that dimensional reduction things are good, so you can listen to Isaac's talk on Thursday about that. And we also have a Business Finland project to commercialize some of our methodologies, so this BOMP project. So thank you.
Thanks a lot, Tero. Do we have any questions?
So on the metallic glass project, I have a question about, did you consider whether or not the thing is actually likely to form a glass? Because in simulation, it's in simulation, it's hard to crystallize from the melt because you're cooling at well, 1,000 billion Kelvin a second, and to form a glass in an experiment, you're looking at 10,000 Kelvin a second cooling rate.
Yeah, this glass forming ability is basically why we chose this. That it's known that these nicely formed glasses, at least in some range of the composition space, and we tried to restrict ourselves roughly to that part. We have an ongoing project trying to dig deeper into this glass forming ability thing, but not here. We just assume that these form nice glasses, and we check that in the simulations at least they are glasses.
Okay, do we have any further? Yes.
Thank you for your talk. I'm not really familiar with the LAMPS simulations of these kinds of materials. How do the potentials, how well do the potentials work and reproduce? Like, these are really complex systems, right? It's studied even with first principles. So I was kind of curious what potentials you used. I don't know if you said it. And how accurate are they?
Yeah, I mean, we're not qualified to say how accurate they are, but the point why we use these two systems is that there's availability of potentials. So people have been studying them, and at least in some range of the composition space, again, if you go to the extreme edges, it might be that the potentials are not ideal, but yeah, that's one thing that why we can't just switch some of these to something else, because then maybe we might not have potentials for that. Of course, people are doing these machine learning things. So.
Sure. Okay, thank you.
Okay, but that's the last one, because then someone needs caffeine.
I'll be fast. Very nice work. Regarding the last thing you hinted at about the icosahedral structures, with all the data that you have collected, aren't you tempted to try to look at, these sort of patterns in the I try to, come up with design rules that can perhaps be applicable beyond the elements that you're studying now?
Yeah, so here we did a very, very simple analysis of this. And compared to the lot of the in silico glass community, I think we now have quite a lot of data to work with, which is a good side product of this whole optimization thing. We haven't discussed doing that yet. We have different things that we are doing, but that would actually be a good idea to try to figure out what would be the optimal structure of how would you design this? Yeah, it's a nice idea.
Okay, with that, I would say let's thank Tero again.
Thanks.
And before everyone is rushing for the coffee, I would ask